In this lecture, we will be learning about the limit comparison test for infinite series. So let's recall the fundamental question that we're working with when we work with infinite series. So we have a sum, and going from, say, 1 to infinity of a sub n, the a sub n's are non-negative for all n bigger than or equal to 1. So we're adding up a bunch of non-negative terms. And the key question we always ask is, does this series converge? That is a way of saying, is the sum finite? And that boils down to the following question, and this is true for any convergence test. So every convergence test that we study is attempting to answer this question. And the question is, do the terms a sub n in your series approach 0 fast enough as n goes to infinity for the sum to be finite? So for this sum to be finite, as you march down the line of terms, these a sub n's need to be approaching 0 at a fast enough rate for the sum to be finite. Approaching 0 is not enough. You need to have them approaching 0, but you need them to be going fast enough. So every convergence test we study is trying to answer this question for a given series. The limit comparison test is such a test. So in this case, suppose you have two series, the sum of a sub n's and the sum of b sub n's. Both are series of non-negative terms for n greater than or equal to 1. And suppose further that the limit of the sequence of the ratio of the terms of a sub n to b sub n, the limit as n goes to infinity of that ratio is equal to some positive constant c. Then the two series exhibit the same type of behavior together. They either both converge or they both diverge. The idea behind this is that if you look at this expression, this limit, and again, this is the limit of a sequence. If you look at this limit, for large n, this is saying that a sub n over b sub n is approximately equal to c. But that means you can multiply both sides by bn. And so for large n, each an is approximately c times bn. And so what that means is that as you move down the terms in this sum, the terms are looking more and more like the constant c times the terms from your sum of the bn's, which is, the idea here is you know what the sum of the bn's does. You know that it converges or you know that it diverges. You establish this limit, and then you can say that the sum of the an's either converges or diverges based on this test. Let's talk about how you actually use this. So the idea here, think of it as we're given the sum from n going from 1 to infinity of a sub n. And we find a simpler series, sum going from n equals 1 to infinity of b sub n, such that the limit as n goes to infinity of the quotient an over bn is a positive constant. And this is important. We know that the sum of the bn's converges. So what you've done is you've started with the series that you're given, the series you're working with. You find a related series that's typically simpler and one that you understand. And if you can tether the two series together with this limit condition, then you can use what you know about the simpler series to determine convergence or divergence of your given series. And again, to come back to the idea here that this is the series that you're given, and by establishing this limit condition, each one of these terms in the series is looking more and more like the constant c times the corresponding term from the series of the b terms. And so as you're adding up these terms, going further and further down the line, the more and more this sum is looking like a sum of c times each of these terms. And that's what causes them to have the same type of behavior. But again, the key thing to recognize is you're given, the way you use this, you're given a series, you find a simpler series that you understand, establish this limit condition, and use what you know about it to conclude convergence or divergence of the ANs. Now, a very common approach here is to choose your simpler series, use what AN looks like for large N. So let's note that. Common approach. Bn, or we select Bn to be the term that AN behaves like for large N. And we'll see that this test is quite a robust test in the sense that, if you recall, we had studied a test called the direct comparison test, where you compared a series that you were given to a simpler series that you understood. This limit comparison test works a little bit more robustly for that type of approach. And we're going to see that in the examples that we'll do in subsequent lectures.